Good morning. Can you hear me? Thanks. This is a new spot for me. Different sound layout. So, let's see. Seems working. Well, this is literally last slide we saw yesterday. I hate when things left unfinished, so let's finish it. First, we need to calculate the position at different time of this object. So, a motion equation, that's a name for any equation which tells us a location of an object at any time. So, if we want to calculate location at x equals 2 seconds, all we need to do is just plug in number 2, take a calculator, and calculate it. So, 48, 2 squared 4, 6, 24, plus 6, 48 minus 24, 24 plus 6, I guess 30. You should check. And of course, you can repeat the same with any number. And then you can sketch a graph as a function of time. The next question is a little bit more elaborated, but we already have almost answered how to do that. So we've managed to relate different constants. These variables, x initial, v initial, a, those are generic, standard variable representing initial position, initial velocity, and acceleration of any object traveling at a constant acceleration. And this is a specific equation. So we matched numbers and coefficients, and that's what we get. We just need to make one more step. The next step is this. For the motion equation, for the quadratic motion equation, the velocity equation is linear. And the numbers now are known, 24 plus, well, this is this plus, but the acceleration is actually negative times time. Time is an independent variable in this equation. V is dependent variable. And of course we can, I think I have one, yeah, so we can write an equation, 24 minus 12 times t. And again, let's say t equals 2. That's going to be 24 minus 12 times 2, 0. And in this particular example, that means this object momentarily stops. The best way to visualize what's happening is actually not drawing graphs. The graph for the velocity as a function of time looks like this. It starts from 24, goes down to 0, but of course goes lower. The best way is to actually draw a motion diagram. So we should imagine there's some kind of a road. Yeah. So we choose positive x direction, of course, to the right. We can select the origin anywhere we like. In that situation, let's finish. Time, x, 0, 6, 1, 24, 2, 30. So at t equals 0, the object was 6 meters away from the tree, from the origin. At t equals 1, the object was 24 meters away. And at t equals 2, the object was actually 30 meters away. But here, it stopped. So velocity here is 0. What does it mean? It doesn't mean it doesn't move anymore. It means now, after this instant, it starts moving back. So for the first 2 seconds, the object was traveling to the right. So the velocity was directed to the right. Here it becomes 0 at this instant. But then the velocity points to the left. That's what is happening. Well, a couple of notes on the lab. Because yesterday I've heard some weird things. You don't have to measure all individual, you just roll the measuring tape and measure all the distances you need. And distance over time gives you average speed. Displacement over time gives you average velocity. That's it. And for reaching out across the open space, you just need to use the right triangle. But the trick is this angle theta should be large enough so at least some value between 30 and 50. Otherwise, the measurement wouldn't be correct. And finally, let's get back on the track, literally. Well, we know already that this is the ultrasonic motion sensor, and this sensor basically represents the measuring tape. So let's check if it works. It does. That's something I didn't think of because I need to be here and there simultaneously. That's impossible. So I need someone to help. You can go both, doesn't matter if you want to. So all I just ask you, just please flip the cart, the green cart over, put it on the rails, and let it go. See, even, okay. So wheels should be in grooves. All right, go ahead. Thank you. So I always recommend to scale up the graphs and oops, wrong, go away. And as we know, go away. We can make a linear fit or quadratic fit. We just have to select regions close to each other. And these numbers now, all right, I will need help a couple of more times. So can you can sit down and take notes and maybe somewhere else So I just want to write down these numbers for you because it's important part of the reasoning. So what I see here, A equals 0.049. I don't care about accuracy. B equals 0.35. And I don't really need C. C depends on where we choose the origin. It doesn't really matter. And here what I see is M equals 0.1 4 and b equals 0.34. Well, the closed loop already tells us these numbers are very close to each other. And we know why they should be close to each other. Because here we have a motion equation, which I would write c plus 0.35 times time plus 0.049 times time squared. And here, that should be a velocity equation, which, again, should start from initial velocity 0.34 plus the slope 0.104 times time. So in this equation, this variable represents the initial velocity, and in this equation, this variable represents the initial velocity. So they have to be close to each other. What about acceleration? Well, the best way to store visual information. This is supposed to be the acceleration. What about this number? This number is not supposed to be equal to the acceleration, because the actual motion equation, as we saw, should look like this. X equals x initial plus v initial times time plus a half of acceleration times time squared. A different question, why is it a half? We can talk about it, but for now it's just a fact. So again, we have to make a conclusion that 1/2 of A should be equal to capital A, this big number, 0.049. So again, from this equation, acceleration is about 0.1. And from this equation, if we multiply by 2, it is again about 0.1. So everything is consistent. And of course, we can use this experiment for calculating those things we have learned: average velocity, average speed, average acceleration. For example, let's take two instances, 0.5 and 1. Yeah. So time, position, velocity. 0.5, position equals 0.3, velocity 0.368. 1, 0.499, I rounded to 0.5, and velocity 0.44. That's all we need. These are data. Now we just have to apply straightforwardly, without any thinking, definitions of those quantities we want to calculate. For example, normally when we write a label for average velocity or average speed, they look alike. So we would have to add some additional indicator for that. There are many ways to do that. Most convenient, most common to indicate the average velocity is adding that symbol x. So it's average velocity relative to the x-axis. And relative to this axis, it could be positive, could be negative, as we saw. If velocity points to the right, it will be positive. To the left, it will be negative. And for the average speed, we usually don't do anything. Or just to make sure we show that it's speed, we'll write speed. All right, now we can write definitions. Delta x over delta t. What is delta x equals to? 0.5 minus 0.3 over 1 minus 0.5. At this time, you just take a calculator and calculate the result, which is 0.2 over 0.5, 0.4. And I don't write units here because they all assume to be meters, seconds, meters per second, which means we use International System of Units, SI, System International. And for the average speed, we need to calculate distance over time. But in this particular experiment, the displacement of this cart from here to here is equal to the distance traveled. So in this situation, there is no difference between average speed and average velocity, 0.4. And finally, average acceleration. Well, for average acceleration, we're going to need using velocities. So acceleration, average, delta V over delta T. So 0.44 minus 0.368 over, again, 1 minus 0.5. Well, I know how to divide by 0.5 at 0.44 minus 0.368 is above my abilities. So it's going to be 0.072 times 2, 0.144 meters per second squared. Okay, that's what I want to write down. Very hard to write accurately on this. That's why I read everything out loud. So you don't have to watch, you can just listen. Well, and of course, if we had time, we would have to repeat similar calculations for different pairs. And turns out, average velocity, of course, would have been different. It travels slower here and faster there. But average acceleration would be the same. And that's just a fact. We can, again, spend extra time and calculate the average acceleration again and again and again and again, and we're going to have exactly the same number, well, plus minus errors. So in that case, as we said, we don't call it average anymore. We just call it acceleration. And because it's the same, we call it constant. And the motion like that, we call motion with constant acceleration. And these equations prove, not theoretically, from experiments, that if your motion equation looks like that, your velocity equation must look like this. Those coefficients must be related the way they are related. There is, of course, a theoretical proof of that, but who cares if we do it experimentally? Now, actually now I can do it myself. So I want to close this layer. I want to erase all data. Because now I just have to push it. And now I'm okay. Well, again, I think it fell off a... It's not a very good parabola, so... Too much friction. Anyway, so this is the part you want to talk about. Oops. I didn't select anything. And so the equation is .28 times time squared minus 1.92 times time plus constant doesn't matter. We can see the difference between this situation and previous situation. The difference is here, not in here. We know that this number is related to acceleration. So if we take this number and multiply by 2, that's supposed to be acceleration. That's supposed to be velocity, well, initial velocity. And turns out now it is negative. Acceleration still is positive, but velocity is negative. How can it be? Well, first of all, now it travels initially against the positive x direction. So the velocity is supposed to be negative. But of course, we also can actually calculate. Again, we can take two consecutive instances, 1 and 1.05. So that will be x1, x2, v average x equals, well, delta x over delta t. Now it's going to be, no, it was moving too slow. The position practically didn't change, so I want to take 1.3 and 1.15, so 2.142 minus 2.143 divided by 1.15 minus 1. So negative 0.001 divided by 0.15. It is negative exactly because, yes? In the lab, yeah. In my example, I do whatever I want to.
Well, it wasn't moving.
Oh, good point. But still, I do whatever I want to. So this is practically 0. 2 seconds, I got to scroll down. I don't want to lose it. So yeah. Can I erase it? Yes, I can. It wants me to close everything. All right, but okay. Yes, selection. Again. Now I can take this and this, this and this. So Vx average 1.77 minus 1.81, 2.15 minus 2.1. And, well, you can see it's negative as it's supposed to. And what I wanted to say is, actually, let's calculate it. Let's calculate it. 1.77 minus 1.81 divided by 0.05, right? Negative 0.8, which is very close to this number. negative 0.75. And this is actually how the velocity is being obtained in this experiment. The software doesn't measure velocity directly. The software measures only position and time. So these are measurable values, but this value is being calculated. How? Well, exactly like I just did, but more accurately. But because this value is related to this tiny interval, so the location of the cart was somewhere here, we don't call it average velocity anymore. We call it instantaneous velocity. And that velocity changes, but we can always calculate it again. We can pick up 2 consecutive time instances and calculate the new velocity. So the velocity which we measure instantly, and we call it instantaneous, is actually the average velocity. But when the time is practically 0. That's it. So if we want to calculate the instantaneous velocity, we just have to pick up 2 very close instances, measure 2 very close locations, and calculate this fraction again and again and again. And that's how these numbers all calculated. Instantaneous. Well, and again, this number, negative velocity, means exactly what we said. The cart was initially traveling opposite to positive x direction. The velocity was directed to the left. Eventually it stops. In this situation, there is location where velocity momentarily becomes 0, like in our example. And what's happening after? It starts moving back to original location. What about acceleration? Well, we saw the number. It's positive. And it is constant. That's what's important. So no matter how the cart was traveling, the acceleration always was directed to the right. But for the first part of the motion, the cart was slowing down. And for the second part of the motion, when it was traveling back, the cart was speeding up. So we have in this experiment 2 cases. First case, when velocity and acceleration are opposite. And we saw that in the result, the object was slowing down. And the second case, when velocity and acceleration point in the same direction, and we saw that in this case, the object was speeding up. All right. Any questions? You know what? One more picture. And we're done with track. Yes?
So how did you want us to write the average speed? Like what's the letter?
Okay. Average speed is a good question. So first, again, slowing down versus speeding up. It's about what is happening to the speed. When speed increases, the object speeding up. When speed decreases, the object slowing down. Speeding up happens when velocity and acceleration point in the same direction. Slowing down happens when velocity and acceleration are opposite. Speeding up, well, I just add arrows, and I'm gonna, so velocity points down. Well, velocity at different locations is different, slower, faster. To indicate that fact, we draw shorter arrow, longer arrow. But acceleration is constant, is the same everywhere. And if we start from, let's say, here, and we end here, this will be our total displacement. Slowing down. So let's say this is the origin. We pushed it up. So initial velocity points up. And over time, it's still moving up, but slower and slower. So in a second, velocity will have smaller magnitude, and eventually it stops at a certain point. After that, the same cart, well, will be moving back to the original location. So velocity now will change like this. What about acceleration? Well, as we said, the acceleration, A is constant and doesn't depend on anything. It always points to the same direction and always has the same length. Now, if I want to calculate average velocity, let's say I start here, I move like this, long time interval, and I catch it here. Average velocity should be equal to still x2 minus x1 over t2 minus t1, nothing else. Average velocity is very simple to find. Speed. What is the definition of speed? Well, you asked the question.
Total distance traveled.
Exactly. Total distance, well, time interval is the same. All right, what is the definition of distance? Length of the trajectory, that's the definition. So, do you see the trajectory here? Yes, the trajectory is shown by the green line. It starts here. It goes up to here where cart stops. We can call it L1, the first portion of the motion. But then it moves from here all the way up to x2. We can call it L2. And what will be the total length? The sum, exactly. So in this situation, average velocity and average speed are different. And now, of course, we should ask the next question, okay, how do we find those distances? Well, this is a very special point. What is so special about it? At this point, velocity momentarily becomes equals 0. That's what we know. That's a point where it stops. So this is a very important piece of information, which means we have to use it. But if we want to use information about velocity, what equation should we use? We have two equations. One has a name, motion equation. Second has a name, velocity equation. If we want to use any information about velocity, what equation do we need to use? Velocity equation. How do we use equation? How do we use an equation? What is the first step? What do you think? Yes? No? No. Do you see any equation here? Write it down, that's the first step. So we write it down, velocity is equal to. Now we can use it. Well, this instant, I don't know, we can call it time stop. Yeah. This instant is so special that when time becomes equal to this instant, velocity becomes equal to 0. This is how we use it. We plug into the written equation variables or values we know. So 0 is equal to initial velocity plus acceleration times time to stop. Well, in our experiment, the initial velocity, well, first of all, it's a negative number, but it's known, so we know it. We know it. So we know that. And we know acceleration because we get those from the data. So in this equation, there's only one unknown, time. So we can solve it for time. And our brain now should keep separately 3 brain cells, one for this because it's an unknown, one for this because it's a known, and one for this because it's also known variables. Even if we use letters, they have slightly different meaning. Something we need to find, something we have known already. What can we do now? Well, now this becomes a known variable. So now we can use it. Everything we have found can be used for the next step. Now, of course, we can use this equation. The position equation, the motion equation. We take this number t and plug it into the motion equation. And because we know this, we know this, we know this, those are constants. By plugging in the time, we're automatically calculating x stop. And that's it. That completes physics. The rest is geometry. How do you find the length number 1? Well, that should be measured from here to here. We know that. We know this. How do we calculate the length number 2? Well, we need to measure this. How do we find this? We plug in total time, calculate this number. So calculating distance traveled might be a very long process, but it's always a process like that. If there is no point of the return, displacement and distance are equal to each other, in that case, everything is clear. But if the object travels, stops, and travels back, in that case, displacement and distance are different. To calculate displacement, we just subtract 2 numbers, x1 minus x2 minus x1. But to calculate distance, we have to make many, many steps like this. Did I answer your question? Any more questions, please? Yes?
Why do we use that equation for velocity instead of the v0 plus 1/2 at? When we do the substitution at the x, that's the one that we use.
I don't understand. What equation do you want to use?
Why not the v equals v0 plus 1/2
This?
below?
This equation we used here. This equation we used here.
Yeah, but why not the one that is 1/2 at?
Because in that equation, I represents only a constant. V is a running variable which represents velocity at any location, at any time, including that time when it stopped. What happened here? This is just a constant. And in this situation, it's not zero. It cannot be zero. We have to use an equation where velocity can be equal to zero. That's the only equation, because eventually it becomes equal to zero. Well, okay. This is the summary of situations when things might be speeding up or slowing down. Yeah. We always point x-axis to the right. So everything which points to the right is positive. Acceleration points to the right is positive. Acceleration points to the left is negative. Same velocity. Now, when velocity and acceleration point in the same direction, object travels faster and faster and faster. Acceleration helps to travel it. When velocity and acceleration are opposite, acceleration slows it down. And actually, there is another name for that process, deceleration. Finally, question. So drivers west. It's a good driver. Instead of speeding up, he slows down. So what is the direction of the acceleration? Just a second. So the motion diagram, of course, is very clear. To indicate the velocity, I need to draw an arrow. In which direction? What does west means to us? Left. And that's initial velocity because it changes. So here we see a deer. And what process is happening? We have to make a choice. Speeding up or slowing down. There's one single word in this text which tells us. What is that word? How do we make a choice? What is that word which tells us what's happening? Yes? Brakes. Yeah, not gas. Brakes. This is a very important example. When we read a problem, different words have different value. Yeah. This is the most important word. It gives us an important information about what will be happening. And to make a connection, we have to use that life experience we have. If we didn't have that life experience, we couldn't answer even this simple question that's about background, right? So brakes means not speeding up, slowing down. And slowing down means acceleration must be, well, opposite versus parallel to velocity. Opposite. So another choice to make, we make that choice. And opposite to the left means what? To the right. That's acceleration. This is the reasoning, detailed reasoning behind every kind of problem we need to solve. Every step we make, every statement we make must have a reason. Any questions? So these are some cases here. Opposite to each other, slowing down. Parallel to each other, speeding up. Slowing down, speeding up. It doesn't have to be a car, anything, a ball, a person. And this is the summary. So the velocity equation for a mathematician looks like this. The slope, y-intercept. The velocity equation for a physicist looks like this. The slope represents acceleration. The y-intercept represents initial velocity. The motion equation for the mathematician, it's a quadratic equation, just constants. For a physicist, C represents the initial position, B represents the initial velocity, and this coefficient is equal to a half of acceleration. So, and depending on combinations of variables, we can have different graphs. Yeah. When acceleration is positive, graph looks like this for the position. When acceleration is negative, something like this. For velocity, when acceleration is positive, straight line up. Acceleration is negative, straight line down. What if acceleration is 0? We still actually can use these equations. Just plug 0 here. That gives you constant velocity. And the motion with constant velocity is just a special case of the motion with constant acceleration, when acceleration is constant and equals 0. Question, please. Is it about mathematics? No. Is it about physics? No. It's a short memory test. In this situation, when motion equation is quadratic, velocity equation is linear, these coefficients, A, capital A, and B, must be related. Well, by now you should make your mind. I want to switch. Well, while you're sending. All right. 6 people told me they've been late. Thank you for your honesty. That was question 2. And this is, yeah. And this is question 3. Answer 2 is correct. Yeah. Because again, this is supposed to be the acceleration from a physical point of view, and this is supposed to be acceleration over 2. So m over a equals acceleration over a half of the acceleration. That's it. Well, let's do some more examples, just more examples, I hope. Graph. How do we use graphs? Well, this is an example for the velocity graph. First, we need to read it. What is happening? Well, the motion starts from the origin, And from the origin, it starts moving either to the right or to the left. The graph tells us. So please, what do you think? If it starts moving from the origin, according to this graph, for the first, let's say, couple of seconds, how does it move? To the right or to the left? Right. You're right, it's to the right. Next question. This question is for you. At t equals 21, 21 seconds is here. What is happening to the object? Is it speeding up or slowing down? So you should choose your answer and enter it. Now, while you're doing that, so again, I always recommend start from picturing what is happening. Taking like a mental snapshot of video. In that case, we first need to add the axis always. So that's the origin, that's 0. And starting from here, it starts moving. How do we know to the right? Well, because velocity is positive. Velocity is positive. So how does it move? It moves actually faster and faster. Low velocity, high velocity. So it is speeding up until it reaches 1, 2, 3, 4, 5, 6, 7 meters per second. 7 meters per second. What is happening next? It keeps traveling? No. Velocity remains 7. It's not 0. Rest means velocity 0. But velocity is 7. But it remains being 7 for a long time. So velocity becomes constant. And remains constant from 3 to 18 for 15 more seconds. So, still 7 meters per second, still traveling. And starting from this point, does it move to the right or to the left? It still moves to the right. The velocity is still positive. But how does it change? High velocity, low velocity. So it's slowing down. That's the right answer, right? And eventually, it stops. Of course, so that's velocity, 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 velocity. Of course, we also can say something about acceleration. Acceleration remains constant and points to the right between 0 and 3 seconds. What about this part? What should we say about acceleration? Anyone? 0. There is no acceleration in life. No means no. In mathematics, no means 0. What about acceleration here? Is it 0? No. How does it point? Now it has to point opposite to velocity. Opposite means left. So that's how we analyze the graph. And of course, quickly, for example, what else can we do? Well, we can plot the graph for, well, the graph for the acceleration is very simple. Yeah. Some positive number, 0, and some negative numbers. How do we find those numbers? Well, acceleration here should be equal to delta v over delta t, 7 minus 0 over 3, 7/3. The acceleration here should be equal to, again, delta v over delta t, 0 minus 7 over 23 minus 18, negative 7/5. So what about the graph for the position as a function of time? Well, theoretically, we know how it should look like. When acceleration is not 0 and positive, it should be a parabola. Then acceleration is 0, but the object keeps moving with constant velocity, should be some kind of a straight line. And then acceleration becomes negative, it's slowing down, so again, a quadratic function, but with branches like this. Eventually it stops. It stops here. So these are important coordinates: 1, 2, 3, or this we can call final. This we can call initial. X initial equals 0. So the easiest way is using motion equation. Yeah? I'm just going to do it once. X1 equals x initial plus v initial times time plus acceleration over 2 times time squared, which is 0 plus 0 times 3 seconds plus 7/3 1/2 times 3 squared, wherever it is, that's the number. Now, this number, x1, becomes initial coordinate for the next part of the motion. Here, that's x2. To calculate x2, I have to start from x1, and I have to add the displacement from here to here, delta x. But how can I calculate it? Well, simple. I can use the same motion equation, but now, for this part, it's even easier because acceleration is 0. So it's only velocity times time. So velocity times time. So x1 plus velocity equals 7, and time between 18 and 3, well, 18 minus 3, wherever it is. And of course, now when we know this, we can calculate the final. Any questions? That's how we plot graphs and use graphs. A specific example. What is happening? I'm going to give you a couple of minutes. Try to draw a picture, a motion diagram. What do you think is happening here? This symbol, V sub-0, people call it V naught. Yeah. It's the same as VI. That's the initial velocity. And the next symbol, V subscript F, is the final. So the initial velocity points to the right. But eventually it stops. It's like with the cart, which was pushed up the incline, eventually it stops. One number is given in the text, 5. This number should relate initial velocity, final velocity, and something else. The first thing to do is to add this number to all given data. So we have to do it literally. Magnitude of the acceleration is 5 meters per second squared. So what symbols do we use for the word magnitude? Exactly. Magnitude of the acceleration is equal to 5 meters per second squared. What we've done is called translation. We've translated a word statement into the algebraic mathematical statement. Ability to make such translations is essential for solving physics problems, because when we read a problem, it's always a text. And when we solve a problem, we always use equations. So this transition, which literally is translation from one language to another language, is an important skill. So we got to practice. Now, motion diagram. I hope you have the same. Positive x direction, always to the right. Origin. And initial velocity points to the right. And final velocity is 0. The object starts, let's say, here. Stops here. Now, equations give us relations. For example, velocity, initial, velocity, time, and acceleration, all connected to each other. How? By the velocity equation. So if we look at this, well, little map, like bridges, technically it tells us we should be able to calculate time because we know three numbers. This. So please calculate time. Yes?
You also calculate time using the equation for acceleration.
I don't know the equation for acceleration.
Well, I mean, just like average acceleration.
Thank you. That's a very good question. Now, I want to show you quickly that this is the same equation. It's like the same person, but you look at, face or from behind. What does it mean in the same? It means that algebraical manipulations can make one equation from another. For example, A times t will be equal to v minus v initial. A will be equal to v minus v initial divided by time, which is delta v over delta t because initial time is 0. So these are exactly the same equations. It's not two different equations. So you can use any. So what do you have for time?
6 seconds.
So 30 plus 5 times time equals 0. 5 times time equals negative 30. Time equals negative 30 over 5. I got negative 6.
I got negative, but then I figured.
So what do you do about it? You just erase the minus? You cannot erase symbols.
I guess I plugged in the acceleration as negative 5. So
Okay, so wrong. Don't do that. That's why it was wrong. That's why you get negative time. And negative time tells you something was wrong. Yes? Yes, we will. But at this time, we talk about time. It cannot be negative. We will. So what step should be done first? Instead of magnitude of acceleration, we have to write the actual value of this acceleration relative to the x-axis. And what number should we write? Negative 5. Because it slows down which means acceleration must point opposite to velocity, which means it has to be negative. You see, these are steps of the reasoning. What is happening? Slowing down. Slowing down means acceleration is opposite to velocity. Opposite to the right means to the left. To the left means negative. Now, we can use the equations correctly. So, first of all, as it was mentioned, absolutely right. We need to convert kilometers per hour into meters per second. Why? Because we cannot use mixed units. We cannot mix kilometers and meters. We cannot mix hours and seconds. So 300 over 36. Anyone? Yes. 8 point, you should speak louder.
8.3 meters per second.
8.3, thank you, meters per second. So now we can write an equation. 8.3 plus -5, technically, times time is equal to 0. Time will be equal to 1.3 over 5, which is 1.3 divided by 5. How do you get 1.3 divided by 5 greater than 8.3? Speak louder. Okay, 8.3 divided by 5. 1.66 seconds. Thank you. So, what is the distance traveled? Why did we need to calculate this time? Well, because now we can calculate the distance. Again, the motion equation. Relates. What does it relate? It relates actual position, instantaneous position, with initial position, with time, with initial velocity, with acceleration. So everything is connected, and now we can just use the numbers. 0 plus 8.3 times 1.66 plus, see, it's a plus. But the acceleration is negative, so we write -5/2 times 1.66 squared. And I'm not going to spend any time for calculating this. Next example. Very similar. So please read, try to visualize. Why is it very similar? Because it's slowing down. But the only difference is now it doesn't stop. So the strategy is supposed to be exactly the same. Initial velocity already is in meters per second. Slows down. Calculate distance traveled. So please transfer all information you need, because I want to switch to a different slide. I want to show a shortcut. As you can see, this calculation for the acceleration already has been done. Acceleration was equal to final velocity minus initial velocity divided by time. So we can use a motion equation to calculate the distance traveled, or oops. So velocity equation, the motion equation, opposition equation, sometimes people call it. Now, I strongly recommend to perform this mathematical exercise. Sometimes we don't really need to use time. In this situation we could, but sometimes we don't really need. When we know velocities and displacement. So mathematical exercise is solving the first equation for time and then plug it in the second equation and then work it out. Algebra, 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 algebra. But as the result, we get a convenient equation which relates final velocity, initial velocity, acceleration, and displacement. This equation has no time anymore in it. For example, since we know final velocity, since we know initial velocity, and we know acceleration, we don't really need time. We could have do it differently. In physics, every problem usually has several possible ways to be solved. So we can use this equation, which has no name. So this is the velocity equation, the fundamental equation for the motion with constant acceleration. This is another fundamental equation, the motion equation. This is not a fundamental. It's like a child of these two. That's why it has no name. But we can use it. So 10 squared, 10. 10 squared has to be equal to 70 squared plus 2 times acceleration is negative times that distance traveled. And now, again, you can solve it for mathematics. Just do a calculator and do it. I'm not going to do that because I want to go through another example. Any questions on this part? So this is math. Math, not math. I think that might be my last example today. Again, let's read it carefully. This problem has 2 parts. Again, it's about a driver. And actually, that could have been me. That happened to me. So you're driving with a constant speed. Suddenly, you see a deer jumping on the road. So, for a normal person, the natural intention is to stop. So you apply the brakes and you slow down. Of course, depending on the situation, you might stop before you reach the deer. You can barely touch it, or you might have been traveling too fast, slowing too slow, and you may hit it. So the question is, what is that critical acceleration? Which brakes should provide in order you would just barely touch the deer, so you wouldn't hurt it. So since the situation has 2 parts, our motion diagram should have 2 parts. So you've been traveling at 20 meters per second. And 60 meters away, so we can set this to 0. That's 60 meters away. You see a deer. And your time reaction, a standard average human time reaction, is 1 second. So for 1 second, you've been just traveling at 20 meters per second. So 1 second. And then you applied the brakes. So after that, your velocity still points to the right, but you're slowing down. So the critical acceleration is achieved when you stop right barely, at the location of the deer. That's it. As long as we have the motion diagram, everything is clear. Here, for 1 second, acceleration is equal to what? 0. There is no acceleration here. So let's call it x1. Yeah. x1 should be equal to the initial x plus velocity times time plus, well, if you want to, you of course can write this part of the equation, but the acceleration is 0 still. So that gives you 20 meters. So you've traveled 20 meters before you applied the brakes. What does it mean? Well, what I like doing, I say, I solved this problem. Now I want to solve a different problem. In this different problem, my origin is here. My final location is here. And what should I write for my new final location with my new origin? Ori. This distance should be equal to 60 minus 20, which is 40. And now we get again a trivial problem about motion with constant acceleration. The initial velocity here is still 20. The final velocity here is 0. The distance traveled is 40. And because we don't care about time, right now we can use that third equation, which has no name. Final velocity squared should be equal to initial velocity squared plus 2 times acceleration times displacement. So 0 should be equal to 20 squared plus 2 times acceleration times 40. Done. It will be negative, of course, because we are slowing down. So the acceleration has to point opposite to velocity, which means to the left, which means negative. It will be equal to negative 400 over 85. Any questions? In that case, we're done for today. Thank you. All right, so what do I need to do with this? Yep.
I was looking on Blackboard and WebAssign, and I didn't notice a grade for attendance for lecture 1. And truth be told is I was one of the folks who actually answered all 12 questions on the first thing. The reason behind that was I was trying to connect to the Wi-Fi. It didn't work.
Yeah, I know. If you sent me an email, I eventually will take care of it. If you haven't sent me an email, you should send me an email.
Okay, I'll send you it. Thanks, Mr. B.
Sure. Yes.
Mr. B, I'm not going to be here tomorrow.
Yeah, you told me, I think.
Tomorrow and next Friday. Those are the only 2 times I'm going to be missing.
Well, you are allowed. Just try to look up lectures online and do the stuff.
All right.
You know. Yes.
Is there a sheet somewhere that has all the equations that we will have on the exam?
The equation sheet for the exam is posted on Blackboard. All of them. For your homework, I recommend making your own equation sheet with extra equations. Usually people print out that one and just adding equations.
And then I was here on the first day, but my Wi-Fi wasn't working, so I couldn't sign in or anything.
Did you send me an email about it or not? If you did, you should send me an email, because someone said, but I didn't have time yet to fix. Yeah.
I was in lab last night, and I left my computer plugged into the bench.
Oh, well, we can check right now. Yeah.
Hello?
What are you looking for?
No, I'm just checking the
All right, let's